Hello everyone. Today I'm going to introduce you to the some of the examples of Mealy machines and Moorey machines with some implementations in the Verilog HTL and the test bench followed by the Verilog HTL. And I welcome you to the day 21 of the training. I'm so excited that every one of you have made this far and some of you are still lagging behind. I can understand due to the exams or due to the natural calamities or some emergencies or somebody have their final year projects as well. So don't get too much confused of many things. One time, one task at a time. So learn consistently and have a happy learning all the time. If you have stuck at any point of the time in this training, just let me know. I'll get a clarification on that topic itself. So let us dive into the today's agenda. Today's agenda is about recap on the Mealy and Moorey machines. FSMs are nothing but finite state machines, as we have discussed in the yesterday's class, and some other implementations of Mealy FSMs are yet to be discussed. Also, with some of the Moorey implementations. When we talk about Mealy, we should talk about Moorey as well. So let us go to the examples. But before that, many of you might have confused due to the yesterday's class and what is this FSM, what is the key role of this FSM in this Verilog HTL, and why do we have to learn this? Should we know this or can we ignore this part? These kind of questions arose when I have explained you. But talking of those FAQs, let us understand by asking these set of questions to the subject. So why do we need FSM implementations? FSM implementations is nothing but if we have inputs and outputs and the functionality, but we don't know the structure or any other logic of the design, then what we are trying to do with the FSM implementations is from out of nowhere, we are deriving the hardware architecture of the functionality that you are getting from the project or from the real time in the team. So whatever the functionality of the architecture is that required, that can be achieved in the hardware realization through the FSM implementations. So let us go with the definitions. In the complex designs for larger number of internal blocks and the elements inside the design, but if there is an unknown circuit design or unknown logics, then we need a structure to derive the design as per the required functionality. That structure is defined as finite state machine. So if we have a black box, but you do have inputs and output, what output is derived or desired of that you are expecting. So what is the output that you want or you are looking for? So for that, achieving that output from the given input, there should be some process inside a internal architecture of the chip. So that architecture is nothing but FSM implementation, finite state machine. So what are we getting? We are getting from the present state, present input, and the next state by these states. That is what FSM implementation is. So in the larger complicated circuits, we only know few of the designs or predefined IP integrators, but we may not know some of the hardware that we want to use or that can be used to connect the known IPs. So there are two sets of hardware realizations. One is very known in terms of IP intellectual property integrations that we take, like memory designs, controllers, or UART protocols, AXB protocols, or any other bus interface. For example, we have took BRAM as an example, and we have developed the processor as well with the BRAM. In the same way, we have some gray area where we don't know the hardware realization in the larger circuit or larger implementation of the project design. For that larger applications on the FPGA chip, what we are considering, we are making an FSM implementation such that this unknown hardware is turned into the known structure. Got it, guys? So that is what FSM implementation is. So next, let us go to the next question. That is, what are the different FSM implementations we have? Usually, for any methodology in the development of any project or any design or any programming code, for that we require some set of rules or set of instructions or some defined methodologies. In that, we have talked about FSM implementation, but how will you implement? That is the question here. So what are the different FSM implementations is nothing but how this FSM implementation is applied or developed, how we are getting the hardware architecture from the FSM implementation. We are getting from Moorey and Mealy FSM implementations. We all know from the yesterday's class, we have understood that Moorey FSM, the output of one state for that output block will be depending on the present state only. But for the Mealy FSM implementations, it depends on both present state and present input directly. That is the reason Mealy FSM can be complex, but it is easy to use and mostly used in the designs. But Moorey FSMs are large. For every single condition or every single transition of the condition, like if A is equal to B, one set of state should be there. If A not equal to B, another set of state should be there. I will show you this kind of complexity in the Moorey FSM in the upcoming diagram. But Mealy, it is easy to implement yet complicated, but you should be very thorough enough. But it is easy to implement in terms of lesser number of states, whereas Moorey FSM implementation requires more number of states. Here states are nothing but data transition or the output transition from one state to another state and to the another state, and it continues to every single change of the condition. So for the functionality, in the inside functionality, we look for conditions. What are the conditions? Depending on the operations and the output and input process, for that process we require conditions to work. For example, in the if-else implementation, if-else loop implementation, or case or case-x implementation, we are looking for conditions. What if A is equal to B, some set of condition, or if X is not equal to Y, some set of another conditions. So based on the conditions, the procedural block works and process begins and ends at the condition statements. So that is a part, but Moorey, take it this way, it only depends on the present state. Hence, for every change of the data or every change that is happening in the Moorey FSM, there will be some other state that should be there for every individual change. But in Mealy FSM, if there are same conditions or same states applying in and here, there will be very lesser states can be used and we can solve the design in a lesser complicated way. So let us go to the next question. What are the states, inputs and outputs in the FSM? Okay, now we know there are two different types of developments in the FSM implementation. One is Moorey FSM and one is Mealy FSM. But in that, what are the components? What are the elements? Now we are talking about hardware architecture, but what are the components of FSM? We know that input and outputs are nothing but present input and present state. The next state generated output after the next state block is nothing but next state. It's nothing but output at this point. Output at this point, and these are all inputs. Present input and present state are inputs. But we can also see present state is also the output of memory block. So quickly a reminder, for FSM, what do we have? We have inputs, outputs, and also clock and reset for memory block. And what are the internal blocks we have? Starting from memory block, next state block, and output block. That's what we are talking about. So I'll explain in the next thing. The states represent the input, output and current or the next value of the data at particular instant of time. So this is given at the input, and present state can be the value, some output that is obtained after the process. So after process happening inside the block, some process happens inside the block. After that process happened, you will get some output, right? That output can be present state. Got it, guys? So at this particular amount of clock period, or at the beginning of the clock period, or at the end of the clock period, do follow my cursor all the time so that I'm repeating just now. At some instant of the clock period, in the middle of some clock period in the entire clock, after some process of time, at that particular point of time, we are getting present state. And at the output instant of clock, and at the output instant of the clock, we are getting output. I mean, whatever the output we are getting, that is output generated. And at the beginning of the clock and at the particular interval of the block, we are giving both present input and present state. You will understand in the diagram later, but these are all the inputs and outputs. You can say present input, present state, and next state are the three states available in the FSM implementations. What is their purpose? Their purpose is nothing but having the value contained at the particular instant of clock. Okay, now come to the next question. What are the blocks in FSM and implementations? What are the blocks there between input and output? We have memory block, next state block, and output block, as I said. So though FSMs are declared because of not knowing the logic of the design or any defined specific digital concept, the entire circuit or the design is represented through the three different blocks of the process between the input and output. You understood, right? We don't know the digital concept or we don't know the logic of the design, but what are we talking? We are creating it. The entire circuit or the design is represented through the three different blocks for the process between the input and output. Likewise, between the input and output, memory block, next state block, and output block. So we'll see it in the diagram. So this is what I'm talking about. The diagram is, we'll see Mealy FSM and Moorey FSM with their implementations. Let us talk about Mealy FSM in at this point of time. So for the Mealy FSM, let us quickly go through the inputs and outputs, the connections between them, and what are the blocks and how they are connected. Very important. First, inputs and outputs. We have present input and output. I will come back to the present state again, but the inputs are, we are giving inputs. This present input can be A and B or C or D. How many number of inputs you want, you can keep. But let us assume it is present input in a bunch. We are making this a generalized design. Okay, present input. And then output is our desired output from the functionality. Whether this entire block should act as a addition bit, like half adder, or entire block should act as ALU, which does all the operations of logical functionality coming from right shift, left shift, addition, subtraction, multiplication, division, or we can have these modulus, or we can compare it greater than, less than, and operator, or operations. You can do the XOR operation, XNOR, any other application with the ALU. Whatever the ALU does, that kind of ALU hardware realization can be made in this entire diagram. So the output should look like ALU design. Okay, and that are the input and outputs. Now coming to the what are the blocks available. the blocks available are next state, memory block, and output block. What is the whole and sole purpose of each block? The purpose is memory block. It's nothing but whatever the data processed, it can be stored, it can be read, or it can be written from written on the memory block and read from the memory block. Okay, so that is the use of it. And for the functionality of memory block, you should always have clock and reset. It can be synchronous or asynchronous. We will think about it later. But for memory block, the functionality is read and write of the data or the process or the storage of the temporary data, some in the data register inside the memory block. So that is the purpose of memory block. Think of this kind. But before that, next state, it can have some functionality. It can have some set of primary defined parameters that can be working on. So based on the conditions of the next state. So for the next state, for example, you have state S0, and if you have state S1, let us think of this. For this, the amount of time this is this, like at 5 nanosecond, and after some period of time at 25th nanosecond, at 25 nanosecond of the clock. Okay, let us think. So between that, the data is changing from one state, one position of the clock to the next state at second position of the clock. But before that, what is the functionality? How it is changing? When is the data transmitted from this state to that state? When it is changing based on the condition of the state. For example, for any 2-bit adder, I'll explain this in the next coming example, but think at this point of clock period you are having one state, and next clock period you are having the second state, and the data goes, the transition is from the present state to the next state. So our question is, what is happening? What is the data that we are getting? And in the next state, what is next state assigned with? So that is what next state is considered for. Output block, you all know. And also here the process happens, next state, in combination with memory block. Okay, the process requires memory block as well. And why do we have output block? Output block is nothing but whatever data you get from here, all the data is pushed forward to the output block, and it decides when to exhibit this output. So you have set of outputs like 1 0 for every bit, 0 1 1 1 0. For every bit you should have one set of output, but at a particular instant of clock period, based on the memory and next state, present state, the output is pushed forward in each singular bits. Okay, so think of this way. What are the purpose of this thing and how these are connected? So you should also think about what are the inputs and outputs of each block. So for the next state block, what are the inputs? Present input. Sorry. What are the inputs? Present input and present state. Okay. What are the outputs of next state? Is next state. Based on this next state, the memory block processed is giving a current state, current input. So it is current input. Sorry about the bad handwriting. It is quite clumsy while we write with the mouse pointer. So in the present state, we are getting a current input for the output block. That is the input. And for that input, we are making some progress and giving some output here based on the conditions here. So conditions, on that conditions we are acquiring the output. So these are internally related and they work parallelly. And also with the clock and reset are the inputs of memory block. To enable the memory or to enable the entire circuit, we should have a clock. It can be one clock or many clocks depending on the circuit you use, but in whole sum, like for 4 or 5 inputs or more than 10 inputs, we are taking only single input as the representation. For the representation purpose I am taking. Likewise, for clock, you might have 3 clocks, 4 clocks, or in the 2 clocks that are not synchronized. But what I am thinking is that I am realizing the memory block with this one single clock, and such that I am virtualizing this entire 3 blocks will be working with the same clock and reset again. Okay, so coming to the example, that example is nothing but Mealy implementation and half adder. Half adder, we have seen the truth table in the last example, right? You have inputs A and B, and you have outputs sum and carry. Based on the sum and carry, you are looking at the states. That is what I am explaining. At the next state, it is interrelated to the output block based on the next state. I mean, what is the next state and what do we get the output? When it is going there, the output is changing from carry 1 to carry 0. Or if it is staying here with the same condition true, the output we are seeing at carry 1 and 0. So for example, let us take the input values of A and B as we usually do with the inputs. When it is 2-bit, we start with 0 0, 0 1, 1 0 and 1 1. Technically, in binary terms, these are the two inputs, but in the decimal format, for understandable hexadecimal or decimal format, you can write it as this is 0, 1, 2 and 3. Okay. Why am I saying this? So I am saying to make you understand, whenever you write a truth table or whenever you see a truth table, understand if it is 2-bit, you start from 0 to 3. And if it is 3-bit, you start from 0 to and end at 7. Why do we end at 7? See how many values we have. 0 1 2 3. We have 4 values. 4. And how many values you have? 2 inputs. And now n is equal to 2. How do we derive based on the number of inputs? If number of inputs are 2, how many number of outputs you get? Outputs are nothing but 2 power n, starting from 0. Let us say you have inputs of 4. So you let us see, you have inputs of 4 for a multiplexer, 4 by 1 multiplexer. You have inputs 4. Okay, you have inputs 4. In the truth table, how many set of values you get? Let us say A, B, C, D. This is the most asked question by many people who are learning, very basic, but I am explaining again. You have 4 inputs, right? You have 4 inputs. Now n is equal to 4. What is 2 power 4? It is 16 inputs. So you can't start from 1 and you can't go to 16. You should start from 0 and you should go to 15. Oh sorry, it is not visible, right? You can't start from 1 to 16. You should start from 0 to 15, because in digital circuits 0 is also a value. Technically it doesn't carry any kind of value, but it should represent at least it is 0, and the endpoint is 15. 15 is nothing but F. 15 in decimal. In hexadecimal it is represented as F. And what is 14? E. 13 D. Likewise, you come back, and what is 10? It is A. Okay, so things apart, you will be writing from 0 0 0 0 and 0 0 0 1. So you should be very familiar when you are getting to the digital circuits or in the VLSI industry. You should be very familiar with these truth table functionalities, writing all of these and working on the functionality or the operation in your specific design or the specific module that you are designing inside the architecture. So you should be familiar with this, all basics, very fundamental. But I'm insisting you to learn from the basics at this point of time, because it is a one shot process. When you learn consistently for one time, it is more than enough. And in the complex situations, for example in the project designs, you will be encountering some vagueness by missing some of the basics or fundamentals. So at that point of time you will feel so confident, and many complicated tasks can be done with a simple implementations and simple error rectifications. And in the Verilog HDL, if you want to correct your mistakes, you should be very strong at very basic. So basics of digital circuits and basics of syntaxes as well, syntax as well. And yeah, now let us come to the Verilog HDL implementation. Our example today is 2-bit Mealy FSM, and we have a truth table of A, B, sum and carry. A, B, sum and carry. And if it is 0, 0, 0, 1, 1, 0 and 1, 1. So when it is 0, both the sum and carry are 0, and if it is 1, 1, sum is 0 and carry is 1. And this is carry is 0 all the time when 1 is high and those are added in a series. So it's an XOR addition, guys. Don't get confused, it's not a normal addition of the binary, it's an XOR addition in the half adder. So now we have took half adder. Okay, so module Mealy 2-bit adder is nothing but clock, reset, A, B, sum and carry. All these are inputs. So you know A and B are inputs, sum and carry are outputs. Okay, fine. Why do we take clock and reset? We don't know the design yet, but clock and reset should be implemented in the sequential elements. So you never know, sequential elements might also be in the state. So for the FSMs, we are standardly considering clock and reset, because in any complex design, when you want to implement in the digital circuits, right, we do consider sequential elements. Like for example, you take flip-flops. For flip-flops, you require clock and also reset for enabling. And if we take some other sequential circuits like flip-flops are the best example, but memory, for that memory we should take clock and reset. Memory is a sequential circuit, right? It depends on the clock and reset, and you should consider them as inputs as well. So take them as inputs, clock and reset and A and B. Take the output. So this is first part, this is second part. Now we are going to talk about reg and parameter, that is third part. Why do we need parameters for the 2-bit input, right? We are talking about two states, one is 0 and another one is 1. Here you can also represent as 1 bit 0, and also you can write 1 bit 1, but instead I have represented it simply 1 and 0 for parameters. If you have more than this kind of states, number of states are increasing, you can take from 0, 0, 0, 1, 1, 0 and 1, 1. You will get the example in the Moorey machine implementation, because we have more number of states depending on it. But as of now we have two inputs and you can take two values. When we have 4 states, you should take 4 inputs, 4 values. Then I mean 4 values starting from 0, 0 to 1, 1. I mean 3. It is 0. So 0 to 3. Okay, that is what we are doing. Okay, in the FSM Verilog HDL implementation, we are not casually doing the block-wise structure, but we have 3 blocks to be designed. 3 blocks functionality or procedural blocks should be defined, right? For that, we are taking next state block and memory block design and output block. This is how you will be writing FSM implementation in the Verilog structure. Typical structure of Verilog HTL in FSM implementation. I am repeating as typical structure of FSM implementation Verilog HTL. So what do we have? We have declaration first. This entire thing is a declaration. You have 3 parts. Fourth part is defining the next state block. In the next state block, we are giving conditions and we are deciding on what is the next state. Okay, so it begins at the input. What are the inputs we have? A and B, that are present inputs. Let us consider this present input as A and B, and present state, that present state is nothing but this one. So at the present state, whatever might be the present state, that next state will be operating, and if any changes come at A and B, like 0 to 1 or any simple changes, the next state block is active. So that next state block is nothing but this always block. So we have a case condition, and if A is equal to 1 and B is equal to 1. Now come to the FSM state machines understanding. We have 2 states, right? For the if A is equal to 1 and B is equal to 1, the condition is here. And how do we represent 2 states only? Based on output. Based on the output. So we have took S0 and S1 as 2 states based on the output. So let me erase few of the things which are confusing. Okay. So how do we decide on only 2 states in the FSM? Some might ask this question. We are deciding the outputs based on the output. So these states, current states are nothing but the outputs based on the carry and sum. What are the outputs for here? We have carry and sum. Look at the truth table. We have all zeros for the carry and 1 at the carry. So there are only true transitions. Either carry is 0 or carry is 1. For that condition, we have took, let us take carry is equal to 1 first. And then, carry is equal to 1 first. And then carry is equal to 0. Got it? So then carry is equal to 0. And then based on the carry is equal to 1 and carry is equal to 0, if we think when carry is 1, sum is equal to 0. Let me write with another color. When carry is equal to 1, sum is equal to 0. When carry is equal to 0, what is the sum called as? Sum can be 0 or sum can be 1. So we never know. But for that S1, for that state, this is one condition and this is one condition. Think of this condition, case. So for this case, for carry is equal to 1 and sum is equal to 0, conditions are both inputs are 1. Right? And if not, if else it go to the second state. Okay. And for that state, what are the conditions? For carry is equal to 0 and sum is equal to 0 or 1, we have 2 conditions. A is equal to B or A not equal to B. You are getting the relation between the states and truth table and the conditions, right? Now think of this condition now. Case begins. What is the current state? Your data is processed and we are getting the output carry is equal to 1 and sum is equal to 0. At what point of time we are getting? If A is equal to 1 and B is equal to 1, next state is equal to 0. So next state is S0. Else ns is equal to 1. So else next state can be 1. Okay, we have come here. So this is 1 and this is 2. And now what are we thinking? For the S1 state, now come to this point. We have reached here at this particular clock period. At this particular clock period, we have discussed this. And next state, at the next state, we are talking about if A is not equal to B. That's what we are talking, right? If A not equal to B, A and B are not equal, or A is equal to 0 and B is equal to 0. A is equal to 0 and B is equal to 0. What are we getting, guys? NS is equal to S1. So next state can be S1. This is third. Else where it should go? It should go to the sum 0. Okay, so what are the conditions now? In these conditions, carry is equal to 0. Carry is 0, fix. But if A not equal to B, sum is 1. If A not equal to B, sum is 1. Else sum is 0. Else sum is 0. Got it? And carry is 0. Think of these two things at some point of time. Carry is equal to 0, sum can be 1. And if carry is equal to 0, sum can be 0 as well. That is the reason we are taking Mealy FSM in a simpler representation. Else if this is not the condition, else some other thing, it should always go to the next state. Okay, now come to the memory block. How the memory block is written? Memory block is written in the next state. We are talking about states, individual states. What are the conditions? That's it, done. We are writing next state in the purpose of writing the states. Okay, come to the memory block. How it is written? This memory block is written in terms of always passage the clock. At the passage of the clock, the memory block is enabled. And if reset means reset is equal to 1. If reset means reset is enabled. When it is enabled, right, all the blocks are including memory block, they should go to the initial position. What is the initial position? S0, that initial position. So whatever the output you are getting, that output is considered to the present state. That present state is S0. By default, if you click on reset, everything should come at S0 and it should think of this 1, 2, 3 and 4. This is how it should work. Okay, Mealy FSM in a loop. Else means reset not equal to 0. Then PS is equal to end. So I also insist you to follow the syntax conditions. Syntax conditions is nothing but whenever you write begin, don't forget to write end, and case, you should be mentioning all these conditions perfectly, or else the next state is having no meaning. So then to the memory block, always at the rate of passage, begin and end the process. If reset, present state is 0, else present state is next state. Whatever the next state given to the memory, that can be taken here, and that next state goes to the output block. Okay, so that is our memory. Even in Mealy or Moorey, the memory block implementation is same. It's common. You should remember this for ease of writing. Then come to the output block, third block. how we are deciding? We are deciding on the conditions, these conditions, and we are deciding on the output. So output is nothing but carry and sum are the output. What are the values of outputs? That we should be familiar with. So we are talking with the conditions and talking about output and outputs only. So always at the rate of inputs begin case of the present state. Based on the present state, output block will be working. Memory block will also work with pause edge of the clock, but next state work with present state as the input and present input as well. Likewise, output block depends on present input and present state. Let me take another color. Output block depends on present input, also present state. That is what Mealy FSM is. Hence, you can see begin the process, end the process. In between, you can write the process and case, end case. With the case, what is the S0 and S1? There are two states. At this S0 and S1, what do we need? Begin and end. Carry is equal to 1, S is equal to 0. That is for case S0 state. But for S1, begin, carry is equal to 0. We are deciding if A not equal to B, sum is equal to 1. Else means A equal to B, sum is equal to 0. If A is equal to B here, sum is equal to 0. Okay. And what else we need to write? Here we can mention if A equal to 1 and B equal to 1. You can mention this as well, if condition, and you can write these two statements with the begin. No matters, but this is an easy representation, not to get too confused. I'm just giving an alternative. And default begin, sum is equal to 0 and carry is equal to 0. That's what we can write. Okay, sum is equal to 0 and carry is equal to 0. That is with end case, end there with the end module. End module is related to the initial definitions of the module. Okay, this is what Mealy FSM. Now let us go to the Moorey FSM. Very simple thing. But before that, let us understand test bench of the Mealy FSM. It is just to test your entire functionality of the FSM. We don't know the hardware architecture, right? Whether this is functionally good, correct output is obtained. We need to check. We need to check with the next state block. And how do we check? When in the initial begin, after declaring the registers and wires, whatever wires and registers are defined here, that can be taken as opposite thing. Wires in the design can be registers now, and registers in the design can be wires here. So all inputs are registers in the design file. You have seen the test bench representation in the previous classes, so I'm just reminding you, recollecting the memory. So registers are nothing but wire and reg, sum and carry. Wire is nothing but register here in the test bench, clock, reset, and A and B are registers. Okay, we don't need to declare input and outputs here. No need of that thing in the test bench. It's an environment. Based on this, initial begin, clock should be 0, reset should be 0, and after 20 nanoseconds, reset should always be 0. Why? Because here in the memory block, reset is not equal to 0, then it is working. Then the output of present state is taking the next state. Got it? In the same way, we are considering the reset 0 for these purposes at the present state. So present state should work. For that present state, to get that present state, here reset should be 0. Then only the test bench simulation works. Okay, after that, reset is equal to end it. But when does the next state block works? Next state block works if the clock is 1. So to make the clock is equal to 1, you can simply write clock is equal to not clock, because here the value of clock is 0. And what is the present value of the clock? You can say not clock represents negation of it. So if it is 0, negation of 0 is 1. Now clock is 1. New clock is 1. Hence, when the clock is enabled, entire circuits will be working fine. Memory block will be working, next state block will be working, and also output block will also be working. So for that, input begin, and in the initial begin, A is equal to 0 and B is equal to 0 based on the truth table you are giving. A is equal to 0, B is equal to 0. A is equal to 0 and B is equal to 1. That's what the input we have to test. For a half bit adder, for the 2-bit adder, we need to check both the inputs 0, 0, 0, 1, 1, 0, 1, 1. For this, for every 40 nanoseconds. And here I also want you to write tick time scale. Represent the time scale every time. Even in the test bench, even you use or if you don't use, but start the Verilog HTL code with the tick time scale 1 nanosecond and 1 picosecond. You need to write it before the module, not inside, not after the module. Before the module representation itself, you can write time scale 1 nanosecond, 1 picosecond. That you need to mention for every design code and also for the test bench code. Okay. After 40 nanoseconds, hash 40 is nothing but after every 40 nanosecond, dollar display and dollar time, state is equal to percentage binary, percentage binary, percentage binary, because we are representing the values A and B, state and sum from the present state, A, B, sum and carry. Inputs and outputs that are defined. So you will see the input. And after that, you need to stop it, stop the process. This is dollar stop. If not dollar, it won't work. So there is a syntax error, guys. So correct it with me. You should be very careful with these kind of system tasks. This is a system task. Okay, that's a system task. And dollar stop, it will stop with the conditions. Now let us take, okay, dollar stop and then end the process, done. But you are doing this in the EDI playground, or you might also do with the Linux servers outside in the designs. Then you need to have a best practice of getting the output waveform by writing initial block with dump file and dump where's function, system tasks. Again, these are system tasks, and dump.vcd and one comma. These are the levels. What are the levels? How many levels you need to write? From where the output should be coming? Output should be coming from the module. This you need to write this here. I'll erase one part. Okay, that can be represented here. Done. End here when you begin, and end module. So I hope you have understood that. This is the test bench how you write for the Mealy FSM. Similar to this, we will quickly walk through the Moorey FSM with slight changes. With only Moorey FSM is nothing but we don't have dependency of the output on the present input. Entire remaining things is same. We don't have the present input implementation. But what is the major difference? It requires more number of state conditions. How it is made? So for every Moorey FSM as well, we need to define the blocks. We will be defining with clock reset A, B and are the inputs, and sum and carry is the output, and input clock and reset input A and B, output reg, sum and carry. So for that reg, what are we taking? Registers as present state and next state for the Moorey FSM. And parameters, we can take 4 states here, but for the 4 states, what are the values? 4 is nothing but 2 power 2. So 2 bit 2 bit 2 bit 2 bit parameter values will be taken for the each state. So S0 is at 0 0 0 1 1 0 and 1 1 based on that. Same way, next state block starts at A, B and present state and A comma B. Okay, and for the case if A is equal to 1 and B is equal to 1, if A is equal to 1 and B is equal to 1, carry is equal to 1 and sum is equal to 1 for this state. So we have seen the truth table. I am writing it again. Same half adder with 2 bit additions. That same hardware can be implemented with the Moorey FSM as well, just to make you understand. So 0 0 0 1, I mean C is sum and D is carry. Sorry, my bad. 1 0 and 1 1. What do we get? 0 1 1 0 0 0 0 1. You should remember this structure all the time. So what are we taking now? We are taking consideration into carry 1 and sum is equal to 0. So our value is carry 1 and sum is equal to 0. Carry 1 and sum is equal to 0. So for that carry 1 and sum is equal to 0, what is the condition? A is equal to 1 and B is equal to 1. Next state will be S0, or else it goes to the next state. At this point of time, we are seeing carry is equal to 0, sum can be 1 or 0. We don't know. For that kind of ambiguity, here sum is equal to, okay, here sum is equal to unknown value. For that unknown value, we are taking 2 other states. If A is not equal to B, we are taking 2 other states and we have separated the final state of the carry is equal to 0 and sum is equal to 0. So now our main aim is carry is equal to 0. Here C is equal to 1 in the initial state, and in the next state C is equal to 0. Done. Good. Very good. But what is S? S can be 0 or S can be 1. Okay. S is equal to 0 and S is equal to 1. Okay, done. For S is equal to 0 and sum is equal to 0 and sum is equal to 1, we are talking about A is not equal to B. So for A is not equal to B, if sum is equal to if A is not equal to B, if sum is equal to 1, then we have next state as S2. So next state can be from the S1, it can be S2. This is 3. C. And else, if A is equal to 0 and B equal to 0, next state can be S3. Else NS is equal to S0. By default, it will go to S0. And we have to represent S2 and S3 separately. For S2, if A is not equal to B, NS is equal to next state. And else, next state is equal to S1. It will go back to the back. So I will take this color. And it will be going back to the else, the previous condition. Likewise, in the S3, what is the condition? A is equal to 0 and B is equal to 0. And if A is equal to 0 and B is equal to 0, we are thinking of next state can be S3. Next state can be S3, or else you should be taking to the S1 at the initial state. Else S1. this can be 7. Okay, default value always it should begin with S0 and it should always end at S0. By if you want to reset, by default it should start at S0. That is the syntax for the case statements as well. Like this you need to end the case. Okay, do remember all these things, and when you begin you need to end. Okay, let's go to the memory block. For the memory block, always at the rate passage of the clock, for always at the rate of passage of the clock, your memory block will be enabled. Okay, if you enable it at the reset, present state should be S0. If you click on reset and reset is enabled, reset is equal to 1. That is the meaning of if reset. Always it should come back to the initial position. Else it depends on the next state. Next state can be S1, next state can be S3, next state can be S2, depending on the conditions. Conditions. These are the conditions. Okay, that is a condition. Depending on the else statement, you can see present state can be an S. And now output block. For the output block, always at the rate of present state. That present state, like in the design, at the present state changes. If this changes, output can be processed. Output block will be processed. So for always at the rate of present state, begin and end. For the begin and end, case, end case with default, we need to declare what are the outputs of each block. Outputs of each block, I mean each state. So S0 output is carry is equal to 1 and sum is 0. So again, typo error. So carry is equal to 1, sum is equal to 0, and S1 can be carry is equal to 0. For the S1, carry is equal to 0. We knew that. But we don't know what is sum. So we don't take that condition. But that condition is taken in S2 and S3. For S3, we have declared sum is 0. And for S2, the sum is 1. Okay. Default sum and carry are 0. In the output block, we are talking about the outputs of the truth table. Right? What are the outputs of the truth table or the half adder? It is sum and carry. Whatever might be the design you are talking about, in the output block, your states should be assigned with the output values. Okay, if you are at the state 3 of the current clock point, you should see the outputs as carry is equal to 0 or sum is equal to 0. If you don't see them, the value is wrong. So sum is equal to 0 and carry is equal to 0. This is how you can end up in the FPGA architecture without knowing the logic design or the digital concept of the functionality of the module or the certain block of the FPGA. Hence, you can see the FSM implementation on the chip. Okay, so this is with Mealy and Moorey FSMs. If you have any questions, just let me know. And thank you for attending this training. And be consistent and happy learning. Thank you.